Hello everyone. So in this class we will be solving the numericals in of this chapter of the NCERT textbook. So let us begin the questions. So in the first question he's saying that a 100 ohm is connected to a 220 volt 50 hertz AC supply. What is the RMS value of the current in the circuit? So you know that the RMS current in this circuit is nothing but VRMS by R. So obviously this value is given in this form. This is nothing but RMS value. So it is 220 volts upon the resistance is 100 ohms. So obviously you get this as 2.2 ohms. So this was the A part. In the B part, he is asking that what is the net power consumed over a full cycle. So what is the net power over a full cycle? We call it as average power also, and it is given as IRMS square R, or alternatively we can use this formula as well. So any one of the formula you can use. Anyway, if I take suppose IRMS square into R, it is nothing, oh, sorry, this is your current. So obviously you get the RMS current as 2.2 ampere. So RMS current is square into the resistance, which is 100. So this is nothing but 4.84. 4.84 into 100. So this comes out to be 484 watts. So this is the power. In the 7.2 question, he is asking the peak voltage of an AC supply is 300 volts. It means he is giving the VM value here. He is mentioning if a general value is given and the questioner is not specifying which value is this, it means you have to take it as RMS value. But here he is specifically mentioning that the peak value is this. So you have to assume this is the peak value. Otherwise, if you have not mentioned, if you have just said that the voltage of an AC supply is like 300 volts, in that case you will take it as the RMS. But here he is mentioning peak voltage, so you will take it as the peak voltage. Now he is asking about the RMS voltage. So you know that RMS is nothing but 3m by root 2. So if you calculate this 1.1 times, if you divide this voltage, it will be around 200 to 12 volts. So this is the thing. You will find RMS from this. In the B part is asking the RMS value current in this circuit is 10 ampere. Now it is asking the reverse. Now it is giving the RMS current as 10 ampere. So what is maximum current? RMS current is Im by root 2. So you can find Im is equal to IRMS into root 2, which is 10 root 2. So if you 1.41 into 10 times, that means 14.1 ampere. So this is a kind of a problem they can ask. Now let us take the next problem 7.3. 44 millihenry inductor is connected to this AC supply. Determine the RMS value of the current in the circuit. So observe that he is specifying an inductor and an AC supply. So this is a pure inductive case. This is a question related to the pure inductive case. So in pure inductive case, he is asking about the RMS current. So RMS current is nothing but VRMS, and since it is an inductive circuit, we will take the reactance here. So VRMS is giving us the 220 volt, and the reactance is nothing but omega L. So specifically I can write this. Omega can be written as 2 pi F into L. So this is nothing but 220 upon 2 pi into F is given is 50 na, 50 hertz AC supplies 50 into L. What L is giving? He is giving 44 into 10 to the power minus 3 because millihenry. So if you get 102 point, so how can you calculate this? So this will be 100 pi 2.2, 2.2, and if you multiply this by 10, so, it will be 20. So 1 upon 105 is there, so pi. So 2 into 10. So 2 into 10 to the power minus 2. So this is nothing but also pi is there. Okay. So this is nothing but 100 by 2 pi, which is nothing but 50 by pi. So if you calculate this 50 by pi, if you solve, so can 50 by pi, it means somewhere around 16 ampere you will be getting. Anyway, this is the current. And similarly, in the 7.4 question also, read the question. 60 microfarad capacitor is connected to a 110 volt 60 hertz. Determine the RMS value of the current in the circuit. So this is very direct. Again, in this case, since instead of XL you will be taking XC, because this is a pure capacitive circuit is given. So XC is nothing but 1 by omega C, which is 1 by 2 pi FC. So apply this formula and put this into this, you will get the RMS value of the current in this 7.4 question. Now what is asking 7.5? In the above two exercises, what is the net power absorbed by each circuit over a complete cycle? So this is pretty straightforward also. Let me rub now. You know that the average power is 0. Okay. So in this question 7.5, he is asking about what is the net power. So net power, you know, for a pure inductive circuit, pure L circuit and a pure LC circuit, pure inductive and a pure capacitive circuit, the average power over a consumed over cycle is 0. Why? Because if suppose if I am taking the case of an inductor, so the power, and in L and C case if I take, the power is like this. Okay, we studied also. So sinusoidal was the power, but double the frequency of the supply. So this kind of sinusoidal power we were getting. So if I calculate the average of this, so this area, this is plus area, minus area, plus area, minus area, this whole gets cancelled, and over a cycle, if I say suppose up to pi one cycle is complete, this positive area gets cancelled by negative area, and thus the average power is 0 in both the case. Okay, also you can write from this also, because since what is the general formula for power? It is average power is nothing but VRMS IRMS cos of phi, where phi is the power factor angle. I said you are cos phi is the power factor. Power factor angle means the phase difference angle between V and I, and you know that V and I, in inductive case the current lags by 90 degree, and capacitive case it leads by 90 degree. Either case the phi angle will be 90 degrees, so it means V RMS I RMS cos of 90 degree, and cos 90 is what? It is 0. So what you get? Average power, it is 0. So this can also be an explanation if we asking the explanation. So you can explain them in this particular way. So let us now quickly move to the next question. What is asking in the next question? Obtain the resonant frequency of a circuit where what is giving? LCR circuit with L equal to this much, C equal to this, R equal to this, and Q value. So this is also a very direct question. We have derived the formula. You can easily write the, you can easily just use the formula and get the answer. So resonant frequency is nothing but 1 by root LC. So you solve this, it is nothing but under root of L is 2 and C is 32 into 10 to the power minus 6. And so this is pretty much, and you need to, this is gonna be your omega r square. Okay, this is your omega r square. So omega r square is nothing but 64 into 10 to the power minus 6, which is, you can say 10 to the power 6 by 64. So omega r is equal to root over 10 to the power 6 by 64. So this is nothing but denominator 8, and this pretty much like this. Okay, 100 10 to the power 6 root is nothing but 10 to the power 3, that is 1000. So if you are going to divide this by 8, you will be getting 125 radian per second. So this you get as omega r. Now you need to find what is asking Q. So Q, you know this, omega r L by R. This formula you need to remember. Alternatively, you can solve by this also, because RC also, all this also given. So if I go by this, omega r is 125, L is giving 2 henries, and resistance is 10 ohm. So this is 2 5s are 10 and this is nothing but 25. So this is your quality factor, this is your resonant frequency. So let us move to the next question. These are pretty much direct questions, and in CBSE these kind of questions will be asked. You need to remember and directly apply the formula. These are pretty easy to solve. Numericals, your preference must be numericals first because these are very much scoring. Full marks you can score easily. So let us now move to the next question. That's it, 7.7 question. And what is saying, a charge 30 microfarad capacitor is connected to a 27 millihenry inductor. What is the angular frequency of free oscillations of the circuit? Free oscillations, where is coming from? Because now you observe that this is a LC circuit. He is giving the C, he is giving you the L. So he is giving the C as 30 microfarad and it's giving L as 27, giving L as 27 millihenry. So this is an example of an LC circuit where some charge must have been there. Whatever he is asking, the free oscillations. So free oscillations, you know, omega naught equal to 1 by root LC. Because we compared that with the equation of simple harmonic oscillation, simple harmonic motion of a spring we considered there, and we got the compared those formula, and we found out to be this should be the frequency of oscillation. So you just apply this. So omega naught is equal to LC 13 to 10 to the power minus 6 into 27 into 10 to the power minus 3. So I can say, if I am not, I will just remove the root, so that let us consider omega naught square this. Okay, omega naught square equal to 1 by LC. Whatever. I am solving this first so that you can easily and find under root later on. Because see, if you multiply, it is nothing but 810, 30 into 27 into 10 to the power minus 9, which is equal to 10 to the power 9 upon 80, 810. Or you can write this as 10 to the power 8 by 81. So now if I find the under root of this, so 10 to the power 8 under root is nothing but 40, 10 to the power 4. So, and upon 81 under root is 9. So 1, 1, 1 and 1, I guess, 0.1 radian per second. Alternatively, in scientific notation, you can just read this kind of figure in scientific notation. They write the scientific notation is what? This a 0.0 something and then in the powers of 10. So if I move this by here, it is 10 to the power 3 radian per second, whatever. So the general concept is, this formula is important. Nothing we have done, just applied and solved the question. Now this is the frequency. Okay, what is asking? So now let us see the next question. Now let us move quickly to 7.8. Suppose the initial charge on the capacitor in exercise 7.7. Okay, is related to this. So let us, this is not 7.8, so is related to the previous. What is the total energy stored in the circuit initially? Okay, 7.7, sorry, 7.8, I guess. Suppose the initial charge on the capacitor is 6 millicoulomb. Now what is saying, this QM, the initial charge on this capacitor is mentioned to be as 6 millicoulombs. What is the total energy stored in the circuit initially, and what is the total energy at later time? So you know that initially the charge will be, when t equal to 0, we considered this LC circuit and we saw that when at t equal to 0, all the charge is here only. At t equal to 0, the charge is not getting depleted, there is no current in the circuit, so all the charge is within the capacitor. So that time the electrostatic energy was maximum. Okay, the electrostatic energy was maximum. Static means no motion of charges, no current is flowing at that time. So electrostatic energy is maximum initially. Okay, he's asking the initial condition. So initial condition, electrostatic energy is maximum, and electrostatic energy was given by what it was given by? It is nothing but q square by 2c. That is this q square by 2c. This is nothing but electrostatic energy. So 6 millicoulomb square, this qm2 square upon 2, and c is nothing but 2 into 32 into 10 to the power minus 6. So obviously if you calculate this, it is 10 to the power minus 6 by 2 into 32 into 10 to the power minus 6. This gets cancelled out. So 4 9 ja, and this is 4 8 ja, and this is 2. So this is 9 by 16. So if you calculate this, it is coming out to be 16 times. So if you calculate this, here it is approximately 0.5, it is 0.59, approximately 0.6 joule, whatever. So the point is that how you find the electrostatic energy. So now he is saying what is the total energy at later time. See, this is important. You have got the energy is 0.62 joule. Now he is telling you that what is the energy at later time. See, first of all, here no losses are considered. Since here no losses are considered, it means what? You know this energy remains conserved. Okay. Conservation of energy tells energy will not be created nor be destroyed. It can only be transferred from one form to another. So although at different levels of time this electrostatic energy will be converting into electromagnetic energy and back to electrostatic energy, that cycle will continue. But the total energy will remain constant. Okay, the total energy will be the sum of both the energy electrostatic plus electromagnetic. This both energy will be same. So if 0.6 joule was the initial energy, at a later time the energy also will be 0.6 joule. The sum will never change. The total energy circuit will remain conserved. So this is the principle. So the answer will be the same, that is 0.6 joule. Okay, this is the concept. So now let us move to the next question. So these are just general conceptual questions are there. Some are directly numerical, some are conceptual questions. So conceptual questions we need to see that we can solve it in just a while if we know the concept, otherwise they create trouble. Okay, we will be stuck if you don't know the concepts clearly. Let us go to the next problem. He is saying 7.9, a series LCR circuit R is equal to this, L is equal to this, C is equal to this is connected to a variable frequency 200 volt AC supply. Okay, V is equal to 200 volt and this is variable frequency. Okay, variable hertz, I write variable frequency. When the frequency, variable frequency in the meaning, he is meaning that this is not constant, this is AC supply. Okay, AC supply, that is the meaning. This is not a DC supply. Variable frequency, you need to understand that he is not mentioning directly. This is a term you should understand AC. How you can understand AC? In AC there is frequency only. So variable frequency means this is an AC supply. Already is mentioning. He can write is connected to a variable frequency of 200 volt. Variable frequency supply of 200 volts. If he doesn't mention AC, it means that variable frequency means AC supply. Okay, whatever. Whenever the frequency of the supply equals to the natural frequency of the circuit. So he is directly mentioning this is the resonance condition. The frequency of the supply equal to the natural frequency of circuit. This is the definition of resonance. When the supply frequency becomes equal to the natural frequency. What is natural frequency of this RLC series circuit? 1 by root LC. And this is the condition for resonance. This is nothing but resonance frequency. So the natural frequency, this variable frequency, if becomes equal to 1 by root LC. It means this is a resonant condition. What is the average? What is asking? What is the average power transfer to the circuit in one complete cycle? So this is pretty much a very good question. You need to understand that this is a resonance condition first of all. Okay, this is a resonance condition, and you know what? In resonance condition, if you calculate I, it is equal to V by Z, which is R square plus XL minus XC whole square under root. But at resonance, what you know? XL is equal to XC. You know this? I told you to remember this condition. Otherwise, XL is equal to XC means this part is 0. So what is the value of IRMS? It is V by nothing but R. Okay, this becomes the condition. So I, if you calculate from here, it is nothing but voltage is given to be 200 volts RMS and R is also given, which is equal to 20 ohms. So 200 by 20 is nothing but 10 amperes. And now he is asking what is the average power transferred to the circuit in one complete cycle. So you need to remember this. In average power here is what? In a resonance condition, IXL and IXC, if you consider what we understood, all the, since I extraction becomes like this, okay, and the power becomes now what? Simply you can understand this. This whole was Z. Okay. If I calculate power, I can say I square Z is the power. Okay. But since Z is equal to what here? R. This term became 0. Z is equal to R. So what is the power? Is nothing but I square R in this case, which will only be dissipated, which will only be transferred, because this capacitance inductors will not be consuming, and they will, the voltage drop across both the capacitance and voltage will be, capacitance and inductance will be cancelled out. So P equal to I square R means 10 square into 20 ohms. This is nothing but 100 into 20, which is nothing but 2000 watts or 2 kilowatt. So this is a solution. Okay, remember this. In a resonant condition, this you can also remember that XL is equal to XC. Since XL is equal to XC, Z becomes equal to R. Since Z becomes equal to R, so I is equal to now V by R. Okay, and if you power, if you need to find power, will be only across the resistor, which is I square R or V square by R. This can also be valid, because here what happens, no, this is a, you can understand this condition very well also. Like, let us understand some more concepts here. What I am telling is, in this condition, this suppose this is the I, and this will be VR suppose, and in resonance what happens is, this is suppose VL and this is VC, because current is lagging this. What happens, these two phasors are equal and opposite. XL is equal to XC, and this is series circuit. So in series circuit, current is same, R, L, C. Okay, current will be same. So current is I to all these elements. So the voltage is IXL here. Here the voltage is XC, IXC. So these two voltages are like this, and but they are magnitude XL equal to XC. That means IXL equal to IXC. That is VL is equal to VC. But if we are talking of the magnitude here, they are opposite 180 degree. Okay, the angle of this, suppose VL is something at angle A. The VC will be at angle minus A. So these are opposite. So this will get cancelled out. Okay, if we consider the phasor direction also, this is like this. VL equal to minus VC. IXL equal to minus XC. So the sum of these voltages will be 0. So total voltage is what? VR plus VL plus VC. So this VL VC equal to 0. Now VL, so total V becomes equal to VR only. Okay, so this is the concept. That net voltage drop will be occurring across the resistor only, and the power will also be dissipated across the resistor only. That's why we say that unity power factor. Phi angle is, current is in phase in the resonance case. Okay, so this is the condition here. Now let us move on to the next question quickly, which is your 7 point. We are solving. So now Let us go to the next question. 7.10 we need to solve. A radio can tune over the frequency range of a portion of megawatt broadcast band. Okay, the band is talking power megawatt. Okay, 800 kilohertz to 800 kilohertz to 1200 kilohertz. If the LC circuit has an effective inductance of 200 microhenry, what must be the range of its variable capacitor? So he is asking that we have frequencies range from 800 kilohertz to 1200 kilohertz. Okay, and what he is giving? If the LC circuit has an effective inductance of, now he is in the obviously inductance of the circuit is given as 200 microhenry, and is asking us the what was the range of its variable capacitor. Okay, so the question is we need to find is C variable values. So he is saying that radio is tuning from 800 kilohertz to 1200 kilohertz. Okay, so between these frequency there might be different, some channels might be there or whatever, you need to tune into that channels. So for tuning the channel, what you need to understand that the whatever the input frequency is coming to the radio, okay, this signal frequency, suppose this signal is coming and the signal frequency is suppose f, for example, then what you need to tune, if the natural frequency, the L and C parts are here in this radio, so this frequency of this must be matched to this, then only you will hear the channel. Okay, hear the signal, hear the channel, more appropriately you will hear the channel, then only. So what condition is that? That is resonance condition. So omega of the incoming signal must be equal to 1 by root LC. Anyway, he is giving in the terms of f, so we can write that 2 pi f, okay, is equal to 1 by root LC, and we need to find the value of C here. So if I square both the sides, so I will get 4 pi square f square equal to 1 by LC. So this implies that if I need to find C, I can write 1 upon 4 pi square f square L. So this you can find the value of C. So he is asking me the variable capacitor. So for each value frequency from 800 kilohertz to 1200 kilohertz, you must have a range of capacitance so that you can match the frequency of this LC to this frequency of the radio signal by varying C. So C must have some range. Okay, each and every frequency from 800 kilohertz to 1200 kilohertz must be tunable. For that to occur, your system radio frequency must be capable of matching the frequency of 800 to 1200 kilohertz. Since the L value is fixed, so you are left with C. So you have to vary C. So for C1, suppose C1 we say for 800 kilohertz, for C 800 kilohertz, we can find as 1 upon 4 pi square, and f, it is what, 800 square, kilo is there, so 10 to the power 6, and L value is there, that is 200 into 10 to the power minus 6. So ultimately these are going to be cancelled out, and you can calculate the value of this. You will get the value of C for 800 kilohertz here. Okay, that's not dive into that, just you can calculate that, that is not that issue. Another, you can just find this also, 200 kilohertz. So just you will need to replace this, calculate this, you must calculate this, 1200 kilohertz. Okay, this is square into L is 200 into 10 to the power minus 6. So whatever you calculate, this is the value for 200 kilohertz. So the variable capacitor range is from this value to this value. Okay, so you must have a range of these two so that you can tune into the each and every frequency lying between this. Okay, so this is the question. Let us move to the next question. He is giving a circuit here. Next question, series LCR circuit he is giving. Let us see this question, which is 7.11 question. What he is giving? Let us see. So in the question is saying this is probably the last question we will be taking in this class. Additional exercise we will be seeing in the next class. Okay, so 7.11 question. Figure this shows the LCR series circuit. Frequency, variable frequency. Okay, he's not mentioning the frequency here, but he's giving the RMS value of voltage 230 volt. L is this much, C is this much, R is this much. Okay, first part is determine the source frequency which drives the circuit in resonance. Obviously, omega R is equal to 1 by root LC. Obviously, you calculate this 5 into 80 into 10 to the power 10 to the power minus 6. This is nothing but your omega R square. So 5 is nothing but 40 and 400 10 to the power 6. This is omega R square. Omega R square is so you can find the omega R taking the under root of this. So this is nothing but 10 to the power 3 upon 20. This is 1000 by 20. So this is nothing but 50. So 50 radian per second you are getting as the frequency of resonance, this much. Now B part, what is he asking? Obtain the impedance of the circuit and the amplitude of current. Obtain the impedance of the circuit and the amplitude of the current at the resonant frequency. So what is asking about the impedance? You know impedance is equal to R square plus whatever XL minus XC whole square, and this is going to be your under root. This is the value of Z. So XL is what? XL is nothing but, since we are taking this at, need to find the resonant frequency. Obviously at resonant frequency you know XL minus XC, XL equal to XC. So obviously XL minus XC you will be getting as 0. Obviously the value of impedance will be equal to resistance, but for let us see for with calculation also. So XL is nothing but omega R into L. So this is 50 into L is what? 5 henries. This is nothing but 250. Omega ohms. Reactance in ohm also. And XC, if I say, it is 1 by omega R C, which is 1 by 50 into, and C is nothing but 80 microfarad. So 80 into 10 to the power minus 6. Okay, so this is nothing but 10 to the power 6 upon 50 into 80, or 10 to the power 4 by 40, or this is 1000 by 4. So this is nothing but the 8 520 250 ohms. So you can see that both these are coming to be equal. So if I write here 250 minus 250 is 0. So Z is equal to R square under root. This is equal to R, which is equal to, what is the value of R? 40 ohms simply. Okay. Anyway, I just solved here, but you can also write theoretically that since at resonance condition XL equal to XC, that's why this term reduces to 0, so Z becomes equal to R. That was the case we solved that question also. So now let us move to the next question, next part of this question. The next part of the question, what is saying? Determine the RMS potential drop across the elements okay, of the circuit. Okay. Now he is trying to verify all the results that you must remember actually by this problem. He is asking the RMS potential across the 3 elements. So obviously this is your R. Let us understand it with the graph also. This is, suppose we say VR, this is VL, this is VC. VR is nothing but I into R. Obviously the current is same, series circuit. So VL is equal to IXL VC equal to IXC. So XL we found out to be 250 ohm, which was also equal to your XC. And R you know that 40 ohms. So VR you get it as 40 into what is the current? Okay, current you need to find out. We haven't found out the current, I guess. Yes. So current was easy. So you know that in a resonance circuit, I is equal to V by Z, but Z is equal to R. So this is equal to V. What is V? 230 volt. What is R? 40. So what are you getting? I it as 4, 5, something like that. You need to calculate the current here. So that much the current will be flowing in this circuit. So its value is nothing but 230 volt is the RMS value given. And the resistance is 40 ohms. So this gets cancelled out. So this is 20 and 3 remains. So 7 28 and 2 again. Like this, suppose 5.75 ampere is the current. Obviously, now you calculate what is now VL. VL is nothing but this 5.75 into XL, which was 250 ohms, or you calculate this, and VC is nothing but also 5.75 into 250. So this is what you are going to get the value of this. And suppose observe that the VL and VC magnitude are same. Okay. And VR you will be getting as I into R, which is equal to 5.75. Okay. Into what is the resistance? Resistance is nothing but 40. So again you are multiplying by this voltage will be 230 volts. So the point is that whatever the supply voltage you were giving, it was 240 volt RMS only in the question. See this. If the condition becomes that the resonance, you can observe that all of the voltage is being applied at 230 volt. Now, you know from this, we need to show that the potential drop across the LC combination is 0 at the resonant frequency. Okay. Okay, sir, we will show the resonant. So we can show like this. How we can show? You know that if this is the current I, suppose this is the voltage drop across the R, which will be in phase, and inductor the voltage will be completely leading as the current is lagging. And as we know that VL will be equal to VC. So check if there is a calculation mistake, otherwise this is everything is I guess correct only. So VL is equal to VC. That means these two phasors will be equal. VL will be equal to VC. These two are equal, but these are in opposite direction. They will be out of phase 180 degree. So what is happening? This total voltage is not VR plus VL plus VC. This I have already told you. But this VL and VC are 180 degree out of phase. So this term will be VL is equal to minus of VC. If I take minus of VC, these will be superimposed on each other. However, this is VL equal to minus VC. So these two cancel, you get equal to VR. That is why we get the voltage VR as 230 volt, which was equal to the supply voltage 230 volt. And VR we got is 230 volt. And these two voltages are equal and opposite. See there. So we have proved that the sum of voltages in a the total sum of voltages in a resonant condition, the voltage of, when we consider VL plus VC is 0. You can see this phasor diagram. Okay. Anyway, this is the case. So this was about the numericals in this class. We will see these more advanced additional. These are little bit of good exercises as compared to these were the questions we have solved up till now are pretty direct, and these will be some good questions. So we will try to solve all these questions in the next class. Thank you.